Welcome to The Explainer. Today, we're pulling back the curtain, going behind the screen, to explore that super complex, invisible world that just springs to life every single time you click a button online. You know how it feels, right? It feels totally instant, but that one little click, it actually kicks off this lightning-fast chain reaction. So, to really get our heads around what's going on, let's imagine the whole backend system is like this super efficient digital factory. We're going to follow your order every step of the way. Okay, so your click? Think of it like an order ticket that just arrived at the factory's front desk. Simple enough. But here's the catch. For the factory to even know what to do with it, that order has to be written in a language that everyone understands. And that universal language is HTTP, the Hypertext Transfer Protocol. It's basically the standard ordering system for the entire web. It's what lets your browser, which we'll call the client, talk to the website's server and place a really detailed order. Now, here's a super important point about HTTP. It's stateless. What does that mean? Well, it means the server has the memory of a goldfish. It completely forgets who you are the second it replies to your request. So because of this, every single order ticket you send has to have all the information needed to process it from scratch. That includes something called an authentication token, which is basically your digital ID card, proving who you are over and over again with every single click. All right, so the order is accepted. Now it hits the main assembly line. This is really the brains of the operation, where all the core work gets done. But to actually build your order, the assembly line needs to grab all the right parts and information from a huge warehouse. And that warehouse? Well, that's the database. And they usually come in two main flavors. You've got your relational databases, which are super structured, kind of like a perfectly organized parts catalog you'd find in a CRM. Then you have non-relational databases, which are way more flexible. Think of a giant bin of assorted parts. They're perfect for stuff that doesn't fit neatly into boxes, like a blog post. It's really that classic trade-off, right? Perfect, rigid organization versus total flexibility. Okay, check this out. This really shows the factory's limits. Just like any real-world factory, as you get more and more orders coming in, what we call throughput, the time it takes to process each individual order or its latency starts to creep up. At first, it's not a big deal. The increase is pretty slow. But as that system gets closer and closer to its max capacity, boom, that latency can just spike, like dramatically. And this is exactly why engineers are so obsessed with measuring performance. It's because the bottleneck is almost never where you think it is. You might guess the big database warehouse is the slow part, right? But in reality, the thing slowing everything down could be something totally random, like the little machine that prints the shipping labels. You just can't guess your way to a faster system. You have to measure everything. So that brings up a good question. What about the slow jobs? Tasks that take a while, like sending you an email receipt or generating a big report. If you tried to do those on the main assembly line, it would just jam everything up for everybody else. It'd be a total disaster. Well, the factory has a really clever solution for this. A side workshop, just for these background jobs. So when you sign up, for example, the main system does the super critical part, creating your account, and immediately tells you success. But at the same time, it hands off that slower email sending task to a queue. Then a totally separate worker process comes along, picks it up a few moments later, and sends the email. And the best part? You were never blocked. You could just keep on browsing. But these background tasks have to be reliable, right? That's why they're often designed to be idempotent. Now, that's a bit of a fancy word, but all it really means is that a task can be safely run over and over again without causing problems. So let's say the email service is down. The factory can just try sending your welcome email again later without accidentally spamming you 5 times. Or, and this is way more important, it makes sure that if a payment fails and has to be retried, you don't get charged twice. Super crucial stuff. Okay, so our digital factory runs 24/7. And you know what that means. Things are going to break. It's just inevitable. An external service will go down, a database will time out. It happens. And that's exactly why having a really robust quality control and safety system is absolutely 100% essential. The real challenge here is that errors can pop up from literally anywhere. The database connection might drop, that third-party payment service could have an outage, or heck, it could just be a simple bug in the code. So this system can't just cross its fingers and hope for the best. It has to be built with the assumption that things will fail. So let's talk about the first line of defense, monitoring. Think of this as the factory's alarm system. It's constantly watching key metrics, things like error rates or how fast the system is responding. If the number of failed payments suddenly skyrockets, bam, monitoring sounds the alarm and sends an alert straight to the engineers. Okay, the alarm's gone off. What's next? Well, now the engineers dive into the logs. Logs are basically the factory's super detailed daily journal. They record every single important thing that happens. By digging into the logs right around the time the error occurred, they can get all the juicy details: which user was affected, what information they sent, and the exact error message that popped up. And finally, once the alarm's been heard and the journal's been read, the engineers use something called tracing to pinpoint the exact location of the problem. Tracing is incredible. It follows the entire journey of one single request as it zips through every part of the factory, from the front desk to the database to the side workshop and all the way back again. This lets them see precisely which machine on the assembly line is the one that broke down. So, our factory's humming along nicely. But any successful factory has to do two really important things. It has to grow to handle more business, like a huge holiday rush, and it has to be able to upgrade its equipment over time. So the big question is, how does it do all that without just shutting the whole thing down? Well, to handle more traffic, the factory basically has two main strategies for expansion. The first is vertical scaling. This is like swapping out your one assembly machine for a single gigantic, super powerful one. It's pretty straightforward, but it gets really expensive. And think about it. If that one giant machine breaks, the entire factory grinds to a halt. That's a big reason why a lot of modern systems prefer horizontal scaling, which just means adding more normal-sized machines to all work together side by side. And what about when it's time to upgrade the machinery, deploy new code? The system does something called a graceful shutdown. It's a really smart three-step process. First, it stops accepting any new orders at the front desk. Then it patiently waits for every single order that's already on the assembly line to be completely finished. And only then, after all the work is done, does it safely shut down to be replaced by the new, upgraded version. This is so important because it guarantees that no customer's order gets lost in the middle of an update. And really, that is the fundamental question, isn't it? It all comes down to this constant, delicate balancing act happening behind the screen. It's this fascinating world of trade-offs between speed, reliability, and massive scale. It's a complex, invisible dance of engineering that powers our entire digital lives, all happening in the blink of an eye, right after you click.